At this point we will have a basic delay effect audio example. So we are going to use the transfer function that we defined here to implement a basic delay effect. So I'm going to use NumPy, SciPy signal, IPython display to listen to audio, and Librosa to generate some tones. So here's the function called basic delay, and we have our dry mix, our wet mix, our feedback gain, our delay time in seconds, and our sampling frequency, and this is our input signal. So here we convert the delay time in seconds to the number of samples we want to delay. Here we are defining the coefficients of our filter based on the transfer function, and here we are applying the filter with the coefficients. So it's the numerator and the denominator of our transfer function. So a is 1, a bunch of zeros, and then f. So depending on m, there will be a bunch of zeros, and 1 minus m. So this is the denominator. And here we are generating our input signal that is going to be a 440 hertz. We are going to use 24,000 hertz as the sampling frequency, and this is how it sounds, our input signal. So we have a short tone with 440 hertz. Now I'm going to apply this basic delay that was defined here. So it's filtering the input using these filter coefficients. So I'm setting the dry mix to 1, the wet mix to 1, and the feedback gain for 0.5. I'm setting a delay of 0.5 seconds and the same sampling frequency of 24,000 hertz. So this is our output of this basic delay. So we are using this filter approach. So you can observe that it takes quite a time to calculate. So I will just run this cell now that will compute. So now it's finished, and it's not a very efficient way, but it's interesting to see that we can implement this digital delay as a filter using this transfer function here.